Okay, so let's continue in this part two now. In part one, we have seen about what exactly we recalled. Rather, we have recalled that what is an atomic structure. We have seen what do we mean by valence electron in the last shell, and what role do that play. I mean, when is it positive, when it is negative, the cation, the anion, and all those things we have seen, right? We have also seen how a compound is formed. How do you write a compound by using the valency? So that is till where we did, and then we saw a little bit acid and base property of some element. Today, we are going to completely in this class understand the certain trend of this periodic table that we need to know in our syllabus. So to begin with, if you see this periodic table, there is some sort of arrangement made here. Actually, there are different type of periodic tables in a different diagrams. The one here is little different. Okay, so if you look this side, the horizontal wise, then they are all called period. That means technically your helium, so in period, your helium and hydrogen belong to same period. Okay, that's what it means. So then we have the second period where lithium, beryllium, boron, carbon, nitrogen, oxygen all belong to same period. So this is your period one. Just like this, if I talk of your lithium, you talk of your carbon, talk of your oxygen, they all belong to period two, like that. Now, what is the significance of that? The significance of this period is that if it is one, it means it only has one shell. Okay, it has only one shell. Technically, it only has K. If it is two, it means it has two shell, which means it has K and L. Okay, and three means three shell. Like that, it keeps increasing. Three shell. So in other words, the number of shell is increasing actually. So the number of shell increases downward. Okay, downward. Now, this is a very important thing. So for example, lithium is 3. So how will I write lithium? I can write lithium as 2, 1. Okay, so which means Kl. Again, beryllium 2, 2. So only Kl. You see, again say carbon is 2, 4. So only two shells are needed here, K and L. That's how it goes, all of these. So same way in the sodium, for example. So sodium will be like 2, 8, 1. Okay, and this side, if you talk of phosphorus, it will be like a 2, 8, and then 5. So all of them have three shells everywhere till argon, as you see. So that is called your period. Okay. Now, vertically downward, if you see here, vertically downward, if you see, these are called your groups. So group means your valence electron, okay, or valency, technically. So here, hydrogen has a valency of +1. Beryllium has a valency of +2, right? And then your beryllium is nothing but 2, 3. So it has a valency of +3. See, carbon has 4. It can give 4 or take 4. It can do anyway. Okay. And technically it will give 4 actually. It doesn't really like to, or it will share actually. It will like to share. Now nitrogen has your 2, 5. So it can take, you see, so it will become your -2. Correct? Sorry, -3. Oxygen is 2, 6. It will take 2, so -2. Fluorine is 2, 7. So it will take 1, so -1. So here they accept electrons. Okay. And this side, if you see, they donate electron. Donate electron. Now that's a difference there. So hydrogen, then lithium, beryllium, boron. So I will just write in the next page here, so that we all remember this. So point number 1 is we have period horizontally, the elements have same number of shell. Okay. For example, let's go back and see that example once. For example, let's say sodium and phosphorus. Okay. So sodium and phosphorus. So for example, sodium and phosphorus. Okay. Now, sodium atomic number, if you go back there, you will see it is 11 and phosphorus is 15. So sodium is 11, 22, and this is 15 and 30, 31. Sometimes it varies there. So technically, this means that sodium is nothing but 281. So KLM. And phosphorus is 285. Again, KLM. See, so they both have 3 shell, KLM. Hence, they belong to third period or period 3, third period. Okay, like that. Second, we are trying to understand is, vertically downward, which are called your groups. Okay, so technically groups are nothing but in one group, in same group, elements have same valency. In group 1, like let's say one example, let us take from there. So I'm going to talk of lithium and beryllium, for example. Lithium and beryllium. Okay. Lithium and beryllium. Lithium, which has 3, 6. Lithium, we can write it as 2, 1. So which means it can donate 1 electron. So we write lithium as +1. Okay. And this +1 means it is the group 1. Okay. Now, if I take another example here, lithium, beryllium, I said. So if I take beryllium 4, Be8. So technically this will be like 2. So it can donate 2 electrons. Okay. So technically this will have your Be +2. So this becomes, because of +2, it is placed in group 2. Now let us say we take another example here, something at the end we take. So let's say we take here neon. Okay, neon, which has 10. So neon, let us take. So neon, which is 10. So in neon, we write it as 2, 8. So technically, it cannot donate and has 8 electron in last shell. So it is in 8th group. Okay. So this number will actually decide the group here. This number 1 means group 1. Okay. Then 2 means group 2. Then 8 means group 8, like that. So your valence electron decides the group. So technically, your valence electron will decide the group. So valence electron decides the group. Okay, that's a very important thing for us to understand. We'll just highlight this so that you remember and don't forget this. Valence electron decides the group. Now, let us go back and see the third point. Look at the metals here. So alkali metals. Technically, your lithium, lithium, then your sodium, so on till your francium. So till there, you have all these alkali metals. Now, alkali metals technically are nothing but the ones which react very fast. Okay, they react very fast. They are highly reactive actually, highly reactive, and they form hydroxides. For example, sodium hydroxide, potassium hydroxide, like that. The bases it can form. Okay. Then in the second group, if you see here, in the second group, we have alkaline earth metal. Now, why do we use the word earth metal? Because we use the word earth metal because they easily are available in the earth crust actually in the form of oxide. So for example, it is magnesium, so it can be magnesium oxide, calcium, calcium oxide, like that, beryllium, beryllium oxide. So I put that in a form of sentence here. They are found in earth. You see, they are found in earth as their oxide. So it's like a magnesium, so magnesium oxide, like that. And then they can react with water. They can react with water and they can form hydroxide. Okay. They can further react with water and form hydroxide. That's a very big advantage. And once they form hydroxide, then you know that it is a base, right? You very well know that, okay, this is a base, and that's an alkaline. That's why it's also use the word alkaline. Okay. Like that. Right. Now, these are the two things we have seen here so far. Transition metal, technically, we don't have. I mean, these are metals like, they may not be 100% very good metals, but they are metals. They are also actually metals and they have some transition characteristics actually between the metals and that side. Other metals are like, they can exhibit, like aluminum exhibits a lot of properties as, so it shows a lot of property of metal, but not like a very strong metal when it comes, like a malleable ductility on all those things. And then you have the non-metals after that, okay? Then the non-metals. And your fluorine, chlorine, bromine, they are all called halogens. So this is your in 17 number. This is your halogens, actually, okay? And then you have the most stable, very stable elements, and they are all in your 18th number. But the group is actually 8 here. Huh? The group is 8. If I show you one more diagram here, you see it's 18, but the group is actually 8. Okay. Why? Because the valence is 8 electrons. That's why. Hana? So for example, say if I say titanium. Now in this case, it is 22, right? It's 22. So we can write it as 2, 8, 8, 2. Sorry, a 16, 17, 18, and then 4. So because it has a 4 in valence electron, so it belongs to a group 4, like that. Okay. So just the name is given as a 4B or A, but 4 means group 4. Same thing if I see with the manganese. If I see with the manganese here, Mn, which has your 25, and it can be written as 2, 8, 8, 5, right? Sorry, 2, 8, 8, 7. 2, 8, 8, 7. So because the valence electron is 7, so it shows that it should be in group 7. And that's how it comes in the group 7. Okay. Now, I hope this is very clear here, how the groups are placed. Okay. So looking at the valence, based on valence, groups are placed. So based on valence, electron, groups are assigned. Groups are assigned. Okay. Now, coming back again there. We have seen all this. We are not going to at the moment see all this stuff, actinoid and other. We will see in the higher grades. We'll focus on a little bit more in some other properties here. So I've told you already, other metals are not very good conductors, but they are strong, but not like very strong. They're not very good conductor of electricity like copper. So aluminum is not a very good conductor like a copper. That doesn't mean we cannot use aluminum. We use aluminum as a wire, right? But not as very strong conductor as your copper. So that is how you have to remember these points here. And then there are some other properties like transition metals are heavy, their property is very heavy, and then they melt at a very high temperature. The melting points are very high. So their melting points are very high. Melting point is very high. Okay. Then comes halogen. The property of halogen is that they can absorb radiation. That's a very special, property of them actually. And absorb radiation. I'm just going to highlight this word because this is the keyword here. Okay, absorb radiation. All right, and they appear colored. They also appear colored. Okay, and they are reactive and they form salt. When they react, they form salt actually, halogens. So if I go back here, you see, so like Cl forms magnesium chloride, sodium chloride, salt. They all form. Chlorine can help actually to form, chloride. Salts are formed actually like that. So one minute, I'm just going to write something. Yeah, like NaCl or, MgCl2 like that, or zinc Cl2 like that. So you can get salts out of them. Now, this one you can do some research and you can find out, okay, yourself. They're not required in syllabus, not for syllabus, but you can just find out. This is not in syllabus, not in syllabus, okay? But you can extend your knowledge by doing some research. Now, coming to periodic table trend here. So the first trend we are going to understand is ionization. Okay, so we have seen two stages. The third one we are going to see now here is something called ionization. Okay, this is basically the energy required to remove an electron from atom, completely remove it. So if I have to again check a little bit here in the periodic table trend, and if I have to compare, for example, say sodium and phosphorus, or let's say lithium and oxygen, if I compare lithium and oxygen, okay, lithium and oxygen. So I'm going to compare lithium and oxygen. So I have lithium and oxygen. Lithium is 3, oxygen is 8. Technically, it means it is 2, 1. So valence electron is 1. Valence electron is 1. This is your 2, 6. So valence electron is 6. Now, which is easy to actually remove. You see, lithium can actually remove, you can remove easily from lithium compared to oxygen. Why? Because lithium has 1, as lithium has only one electron in valence shell. In valence shell, it is easy to be removed. Right? So ionization energy is less or low. Okay. Whereas on the other hand, your oxygen, if I see, has 6 electrons in valence shell. So it is difficult to remove. Hence, ionization energy is more. Okay. So as number of electrons they increase in the valence shell, so as I will write it another color so that we remember this, as number of electron increase in valence shell, ionization energy increases. Or we can also say that, if atomic number increases, the force of attraction increases. So energy to remove electron also increases. That will be a better way to actually judge. For example, say, if you look at the noble gas, they are already fully filled, right? So noble gas like neon, if I see neon there. So for example, in neon, for neon, which has 10, we write it as, 2A. So it's already fully filled, very stable, right? So maximum energy required to remove electron. So ionization energy is more. Energy is maximum. Like that. And that is why we say that the ionization energy increases this side. Okay, technically increases this side, actually. Right. Ionization energy is also seen here. So you have seen this one just now. Okay, we understood this one. You can also see that it goes up. That's because when you have a hydrogen, okay, let's say hydrogen, and let's take another one there. So hydrogen and let's say potassium. Let's say potassium, okay? I forgot what's the number here. Potassium is in 4, okay. We got to be careful while we place them. So potassium is here, and potassium, is 19, and hydrogen is like 1. So if we look hydrogen compared to potassium, your ionization energy is less for potassium. Why? So that we will understand here a little bit. Also, vertically upward, like potassium, which is 19, has less ionization than hydrogen, which has only 1. Why is it so? Because potassium atomic size is bigger or greater. Why greater? Because it has 4 shells. Okay. So to remove electron from last shell is easy. In hydrogen, we have only 1 shell. So attraction is most. And not easy to be removed compared to potassium. Okay, and that is why that line here, ionization here, has gone up. Okay, so ionization increases this side, you have to remember, and ionization increases upward. Okay, so just like we spoke, hydrogen and potassium, just now we spoke. Okay, like that, like this. So ionization of hydrogen is more than potassium. But when we come this side, here hydrogen is this side, and or say another element as we can take from here. Your lithium and neon. Okay, so lithium and neon. So your lithium compared to neon, neon has 8, lithium has 1. So this has greater ionization compared to lithium. That's right. So it increases. So that's about ionization energy. Okay. Now, coming to electron negativity. Coming to electron negativity. Electron negativity. There are only one tip. Okay. Sorry. 1 minute. Technically, electron negativity is nothing but it deals with, like, to what extent element tends to gain electron, sorry. Element tends to gain electron. So if I compare again, hydrogen, helium, like that, and if I go back to that periodic table, or if I choose anything else, like all the time we are choosing hydrogen only. Let's choose magnesium and sulfur. Magnesium and sulfur. So magnesium is 12, sulfur is 16. So magnesium and sulfur, 12 and 16. Magnesium and sulfur. So magnesium and sulfur, 12 and 16. So technically 12 means 2, 8, 2, and 16 means 2, 8, 6. What does this tell us actually? It tells that it can give 2 electrons easily. Okay. Technically, it can donate, right? And that makes him Mg plus 2. If you look at the sulfur, on the other hand, needs, I'll put the arrow with the 6 because it is more understanding good. Needs 2 more electron. 2 more electron for octet, correct? For octet. So technically, if it needs, then it will be represented as your sulfur minus 2. Okay, like that. So if you look now from here to here, the tendency of accepting electron is increasing. Tendency to accept electron is increasing. Hence, electron negativity is also increasing. Okay. And that is why if you go and look at that chart, your electron negativity is technically increasing this side. Okay. Just like we saw the sulfur and phosphorus example we saw just now. The magnesium and sulfur formula we saw just now. Okay. So it's like Mg plus 2 and sulfur minus 2. So the electron requirement increases this side. So sulfur has more tendency to accept electron. Has more tendency to accept electron. Okay, so has more tendency to accept electron. All right, that's how you understand electronegativity. And the electron negativity increases upward, though we don't need this, but just for your information that it increases upward. Okay, why does electronegativity increase upward? Is because, I will write here. Yeah, so this increases, this electron negativity increases upward. like hydrogen has greater electron tendency compared to let's say potassium, which is 19, right? Now, why is this so? Why is hydrogen having uh, you know, a greater electron negativity compared to potassium? That's because hydrogen size is very small. Size is small and it looks for an electron as it has only one, as it has only one electron. Okay. Potassium size is bigger. Size is bigger. Okay. And once the size is very big, so there's a lot of balance between the positive and negative charge. Size is bigger and there is strong force between protons and electrons. Hence, outside electrons cannot. Hence, it does not look for more electron to be accepted. It doesn't have the tendency. It does not have at all sort of tendency to take electron. Okay, and that is why it increases as we move up. Like you are moving up from your potassium to hydrogen. Okay, increases. So it has low and your hydrogen has high electron negativity. Okay. Right. Now, these were the most important points that we had to know. Electron affinity is something like, technically the energy released when electron is accepted. Okay. So usually we say that, okay, if electron negativity is more than affinity is also more. That's why it has a similar trend like your electron negativity actually. Okay. And coming to atomic radius, if you see here, that's because, you remember the class, this one we wrote here, right? So I don't know if I have another one here. Yes. So when I talk of atomic radius, so because this is like 1, 2, 3, 4, 5, 6. So this is like a shell. So it's like K, this is like a KL, this is like KLM, like that, right? So the size actually keeps increasing. Number of shell keeps increasing. Number of shell keeps increasing. So the atomic radius also increases. Okay. And these are some of the basic understanding we need to have for our periodic trend. So 4 things you should be knowing here. One is your ionization. Okay. 2 is your electron negativity. With that, the electron affinity, because both have similar trend, electron affinity. And third is your atomic radius. Okay. So these are the things that we should be able to identify in the periodic table, technically. Okay. With this, I think the complete trend is over. Okay. And thank you. So please go through the notes. I hope that it will be more clear, right?